tonight we have the opportunity to interchange some experiences from experts from Japan about the seismic protection technologies, especially for building structures. Well, without further ado, welcome again to everybody. I'm going to present next Dr. Giancarlo Flores, head of the Civil Engineering Department here at UTEC, who is going to make the welcoming address.
Good night, everybody. Thank you very much for joining us here. We're extremely excited to have today Professor Kazuo Tamura, and Mr. Akitsugi Muramatsu, both with lots of experience in the design of seismic technology, especially seismic isolators in Japan. And this is a topic where Japan is quite advanced. As you probably know, Japan has more than 1,500 earthquakes every year. It's home to more than 10% of the active volcanoes in the world. So they actually do know a thing or two about isolation technologies. So we're extremely happy to close this cycle of webinars that we have been holding here in Peru, trying to learn about new technologies and how civil engineering is going to be developed into the future by having both Professor Tamura and Muramatsu-san as our guests today. I do appreciate all of you who have been following these webinars from day one. This has been a very challenging year, but we have made the best of it, and we are using it to learn from people all around the world without the need to move to other countries to actually learn. So once again, without further ado, thank you very much, Professor Tamura. Thank you very much, Muramatsu-san, for joining us here today. And thank you very much to all of our audience for joining us here.
Well, thank you very much, Dr. Flores. Next, I'm going to introduce Professor Tamura. He's currently working in the Seismic Design Laboratory in Japan. Dr. Tamura is a cooperation member of the Design Council of Japan since 2014, the managing director of the Japan Academic Network for Disaster Reduction since 2017, and director and member of the Japan Society of Seismic Isolation, JSSI. Dr. Tamura is also a former professor of the Chiba Institute of Technology, and his research focuses mainly on vibration control of structure, involving base isolation, passive damper systems, active mass dampers, the seismic design of a structure, and earthquake disaster prevention. Dr. Tamura has also extensive experience as a designer and manager of different structural projects in Shimizu Corporation. And without further ado, please welcome Professor Tamura.
Thank you very much for your very kind introduction for me. I'm Kazuo Tamura from Japan. I'm very glad to make a presentation today. Thank you very much for giving me this chance today. I will share my slide. It's okay.
Yeah, we are copying your presentation well, Professor Tamura.
I'd like to introduce the development and applications of seismic isolation system for buildings in Japan. As the introduction, I worked for a construction company, Shimizu Corporation, for about 35 years. And then I worked for Chiba Institute of Technology as a professor. I actually retired from that institute 3 years ago. I should say that I am sorry that my English is poor and that you may not fully understand my presentation. If so, it's all my sake. So then let's go to the next. This shows today's topics. In the first, I will talk about the earthquake environment of Japan very briefly. And next, I will describe about the ideas and development of seismic isolation. including an example of research in which myself was engaged. And after that, I will show you the performance of seismic isolated structures in recent large earthquakes. Finally, I will show you an example of recent research topics on seismic isolation, if time permits. Now, I want to start from the earthquake environment of Japan. Japan is a really nice country which has 4 seasons, and there are great many nice, beautiful places. These pictures are all taken by me. And this environment came from varied natural features. We are surrounded by sea, and there are many volcanoes and steep streams. So our country suffers a variety of natural disasters, like these pictures. We are frequently attacked by large tropical storms, typhoons, and large earthquakes. Among these, earthquake is one of the largest natural threats for us. In our country, I always use these figures. There is a proverb which shows 4 things to fear. They are earthquakes, thunder, fire, and fathers. In Japan, and the authority of father was strong in old days. But now father may be replaced to mother. Anyway, earthquakes are the largest natural threats in our life. This figure shows tectonic plate that covers the surface of the earth. And the red dots indicate the point that earthquakes occurred in a certain period. You can understand that Japan is located in the region where 4 plates interact. And a lot of earthquakes occur around Japan. Peru is here. Peru is also located near the earthquake sources. Japan and Peru rarely have common trouble, that is earthquake. Japanese society has been attacked by large earthquakes from ancient times. This drawing shows the earthquake disaster about 160 years ago. The place was called Edo, the old name of Tokyo, the capital of Japan. Many wooden houses were collapsed and fires broke out here and there. From this, you can understand from this figure. But even though earthquakes had frequently hit Japan, people could not understand why an earthquake occurs. And so there is a folk belief, a superstition that a catfish shakes the earth. A catfish is one of fishes. The left figure was drawn by me, and the right figure shows that the catfish is pressed by pressed by a big stone that is called called kanameishi in Japanese, to be stopped shaking the earth. In Japan, modern structural technologies have been applied, developed, and progressed since the late 1800s. However, these structures were often damaged by large earthquakes. The structural systems and seismic design methods have been progressed through the experience of these earthquake disasters. But now, a vast majority of building structures in Japan are designed by the earthquake-proof design method. At the same time, the idea of isolating the structure from earthquake ground motion had been a people's dream. From now, I will talk about ideas and development of seismic isolation. Buildings are, buildings are shaken by the earthquake ground motion, like this figure. The soil under the foundation shakes the buildings, and the building shakes furniture in the building. By inserting isolation layer at the bottom of the building, the shaking amplitude of the building and the furniture will be reduced. This is seismic isolation. Many ideas on seismic isolation have been proposed after past large earthquakes. These are some examples of them. Rolling ball systems and the fail-safe system, a roller and spring system, plate spring system. This can support the building with soft horizontal flexibilities. But these were only ideas and did not apply to actual buildings. But these two ideas have been applied to actual buildings. Left figure shows rocking column systems. The column will rotate during earthquake ground motion applied to the building. And the right figure is a double column system whose inner column can deform flexibly to horizontal direction and with the dampers. And the outer column will restrain inner column's buckling. This building was now exist in Tokyo. The applied building. This method was applied to a building which is now existing in Tokyo, Japan. The development of the laminated rubber bearing shown in this slide enabled us to design seismic isolated building structures as common way. By this device, seismic isolation became popular. And the rubber bearing is composed of thin steel plate and rubber seats. This device can support large buildings' vertical weight, and it can deform horizontally and very flexibly. By inserting the laminated rubber bearings, the structure responds slowly against severe earthquake ground motions. Then the response acceleration is drastically decreased. as the structure. And the structure and the furniture receive little damage. And now I would like to introduce an example of research on seismic isolated building, which I and my colleague conducted several decades ago. No, decades じゃないね。It's not. Maybe 30 years ago. The slide shows the test building at Tohoku University in Japan. The superstructure of the two buildings are the same. Reinforced concrete three-storied structure. The left building is a conventional earthquake-proof designed structure. And the right structure building is a seismic isolated structure with rubber bearings and dampers. These buildings were constructed in the campus of Tohoku University in Japan to demonstrate the effect of the seismic isolation method by direct comparison between conventional one and base isolated one. Actually, I myself made the basic planning and design of the building. As I said, about 30 years ago. These are the pictures of them, recent pictures. And this may be an oil dumper you can see, and the rubber bearings here. This slide shows the example of the observed response waves. The top wave is recorded at the roof of the conventional structure. And the third one is recorded at the roof of seismic isolated structure. The response of seismic isolated building was 36 girls, and about 1/5 of that of the ordinary building. In order to simulate the response motions of the seismic isolated building, the building was idealized into a very simple ramped mass system as shown in this figure, this one. In the figure above, the observed motion and simulated motion almost the same. Using very simple model, we can simulate like this grade. These figures are the mode shapes of the seismic isolated building, which are obtained from the observed wave data using bandpass filter. The left figure shows that the first mode is a rigid-bodied swaying mode you can understand. Maybe the middle one is ground motion predominant mode. And the right one is second mode, shows second mode of the building. In order to evaluate the seismic performance and the ultimate state of an actual seismic isolated building, earthquake simulator test of 1 by 2.5 scale model of the test building. They are conducted. This shows the setup of the model. In the simulator tests, the level of earthquake input motion, the design level, and also ultimate level. Ultimate level means very large amplitude level. We wanted to know the ultimate response properties. The applied maximum shaking level was 60 to 70 centimeter per second in this case. This left side figure illustrates the crack patterns after ultimate level excitation. The truth is that we had wanted to collapse the model, but it was too strong to be collapsed over the capacity of the simulator. The right figure shows the comparison of the force displacement relationships between the tests and their simulations. Good agreement is obtained from the figure. This hysteresis rule was developed by Dr. Kikuchi of Hokkaido University. At that time, he was my colleague. This is a design example of seismic isolated building in early days before the 1995 Kobe earthquake. This building is a computer center building with the total floor area is 10,000 square meters, which was largest in Japan at the completed time, 1990. The building accommodates important computer equipment, and the seismic isolation system was adopted to reduce the seismic response of the computer equipment. High damping laminated rubber bearings are used as isolation devices. The response analysis of the computer equipment were conducted for 3 ways to set up. The result of response analysis showed that the responses of the computer equipment were reduced by adopting seismic isolation to the building structure. This slide shows the damage due to 1995 Kobe earthquake, which hit the big city of Kobe in the morning of January 1995. Kobe city is located in the west part of Japan. The earthquake was so-called inland earthquake that an active fault underneath the city caused. The magnitude was 7.3 by the Meteorological Agency of Japan. More than 6,000 people were killed and more than 100,000 buildings were collapsed. Bridge piers of highways were broken and fire occurs, and so many people lost their lives. At that time, a large seismic isolated building stands to the north of Kobe downtown. The building has just completed, and luckily, seismographs had been installed in the building. The total floor area is about 47,000 square meters, and the superstructure is supported by 120 rubber bearings. This slide shows the observed acceleration waves. The responses of the superstructure were reduced to about 1/3 or 1/4 of those of the foundations. In conventional structures, the earthquake responses are generally amplified by 2 to 3 times as much as the ground level. Therefore, the responses of the seismic isolated structure can be considered to be about 10% of those of conventional buildings. Because the effectiveness of the seismic isolation method was demonstrated successfully by this building, seismic isolated buildings have increased drastically after Kobe earthquake. This slide expresses the change of cumulative number of seismic isolated buildings in Japan. The number steadily increases with the years. There are almost about 5,000 seismic isolated buildings now in Japan. This shows the change of yearly number of seismic isolated buildings. You can see that the number increased after 1995 Kobe earthquake, and yearly number is constantly about 100 to 200. This graph illustrates the use of seismic isolated buildings in Japan. There are many apartment houses which were built with seismic isolation method. And the seismic isolation has been applied to important buildings, such as the disaster prevention center, an evacuation site, a central hospital, a head office building, a museum, and so on. The seismic isolation method has been also applied to existing old and historical buildings as a way of seismic retrofitting or strengthening. These are typical isolation devices, isolators and dampers. As isolators, there are natural rubber bearing, high damping rubber bearing, lead rubber bearing, and slider with elastomer. As the dampers, steel damper, lead damper, and oil dampers. This shows other sliding or rolling devices. Sliding device, sliding bearing, linear bearing, and spherical sliding bearing. This graph expresses the rate of used isolators. NRB is natural rubber bearing, and LRB is lead rubber bearing, and HGR is high damping rubber bearing. These are major three isolators, and slider with elastomer are here. As I have already mentioned, there are now around 5,000 seismic isolated buildings in Japan, and until now, all the isolated buildings which suffered large earthquake ground motion have demonstrated the effectiveness of the seismic isolation. All the isolated buildings have demonstrated its effectiveness in the real actual earthquakes. Recently, seismic isolated buildings whose isolation layer is at the mid-story has become popular. In the case that the use of building differs at the upper floor and lower floors, this type of mid-story isolated structure can be effectively designed. But the balance among the mass stiffness strength of upper structure and lower structure isolation layer is very important. The balance is important. Therefore, the response properties of the mid-story isolated buildings are carefully evaluated in each building case. This is an example that the governmental office was renovated with using seismic isolation retrofitting. The isolation layer was newly built, and many isolators were installed under the building. Maybe these isolators and these existing piles. By using this method, the building was seismically reinforced while using this building. Next, I am going to introduce you the performance of seismic isolated structures and recent large earthquakes by showing examples. Now I'm going to introduce the performance of seismic isolated structures in the 2011 Tohoku earthquake, very big earthquake. The magnitude of this Tohoku earthquake was 9.0, which is the fourth largest earthquake in the world. The size of the fault is about 500 kilometers by 200 kilometers. Almost all of the country, Japan, was shaken by the earthquake. A great many lives were lost due to the huge tsunami. This is earthquake, and this earthquake caused various kinds of serious damage. The strongly shaken area was so broad that great many structures were affected and received various types of damage. In this earthquake, many records of ground motions and responses of some structures were obtained. We have now a large number of seismic isolated buildings in Japan and a lot of seismic isolated buildings equipped with seismographs. This slide, again, the test building at Tohoku University. This slide shows observed response waves and their spectra from the waves at the upper left, this one. The response of the seismic isolated building was about 1/3 of that of the conventional building. The lower right figure shows this one, shows the locus of the displacement of the isolation layer. The maximum displacement was about 12 centimeters in this case. Next seismic isolated building is Ishinomaki Red Cross Hospital building shown in this slide. This building is located in Ishinomaki City, which was struck by a huge tsunami and earthquake. And the shaking amplitude is very large because the distance from the earthquake source is very short. This building played an important role just after the earthquake. Even though the ground shaking was very severe, this seismic isolated building maintained its function as a hospital. A great many injured people received medical treatment in this hospital after the earthquake. The building is supported by natural rubber bearing and the sliding bearing with steel dampers shown in these figures. Steel dampers, steel isolators with steel dampers. This movie, これどうなんだ動かない。ダメですね。And very exciting video cannot work.
Professor Tamura, please press escape and then you will have your mouse back.
Escape.
Yeah, escape once. Yes, press escape once.
Escape one.
Just press escape on your keyboard.
Escape.
Yeah, escape key, the top left key. Escape. ESC.
Okay.
Now you can click on your video. You have your mouse.
Thank you. Thank you. This movie shows the state of the hospital when the earthquake occurred. This was this is an isolated building, but if this building was not isolated, there are more severe condition will be observed. Please pay attention to that. There are no falling down of the filings and computers. Maybe a usual ordinary building was damaged very severely. Then thank you. This figure, these pictures show the locus of the isolated movement recorded on the scratch plate. Scratch plate is this figure explains the scratch plate. The needle pointer is pressed on the scratch plate. Needle pointer is pressed on the scratch plate. By this, you can record the locus of the movement easily. Very cheap displacement gauge. This building is also very important isolated buildings in Ishinomaki fire station. This is also the isolation is worked very well. Then I'm going to talk about seismic isolated buildings located in Tokyo. Tokyo was about 300 kilometers apart from the epicenter of the earthquake. However, the ground shaking was very strong. The observed acceleration is about 150 to 200 GARS. This figure roughly shows the response level of buildings in Tokyo. This right graph shows the roughly earthquake shaking levels. The response level of ordinary building was about 250 to 300 GARS. Here, I'm going to introduce the responses of seismic isolated buildings in Tokyo. There are many seismic isolated buildings in Tokyo. As an example, I will show you this building. I had been worked for Shimizu Corporation and worked in this building. This building is the main building of Shimizu Institute of Technology. The building is supported by 6 red rubber bearings installed on the top of RC columns in the ground floor. The upper right figure shows the observed peak acceleration during the Tohoku earthquake. The peak acceleration on the ground was 140 GARS, and the responses of the seismic isolated structure were reduced by half. A video、これもまたそうですかね。エスケープしたらいい。Can I escape?
もう一回。
Thank you. いかん。間違えた。 people. Ah, it's okay. It's a video camera is set up beside one isolator and successfully recorded the real movement of the isolator. The maximum displacement of the rubber bearing was about 8 centimeters in this building. This is a recorded motion video. Yeah, once again, actual movement, very small movement, but like this. Actually, the building, the upper building was moving. Okay, thank you. Maybe time is past, and as the last example of seismic isolation, I'm going to introduce a seismic retrofit. The National Museum of Western Art was designed by a famous artist, Le Corbusier. The museum was registered as one of the UNESCO World Heritage in 2016. This museum was constructed originally in 1959 based on the conventional earthquake-proof design code at that time. This museum was seismically upgraded in 1998 by applying the seismic isolation system. A new isolation layer was built under the original foundation, and 49 high damping rubber bearings installed under the superstructure. This is the Japan's first seismic isolation retrofit project. This slide shows the observed earthquake responses of the retrofitted museum during the 2011 Tohoku earthquake. The earthquake responses were reduced a lot, like this one, this figure, by isolators. Maybe this is the simulation results by Dr. Kikuchi of Tohoku, Hokkaido University. It's very good, good simulation. So simulated motion and observed motion are almost the same. One more, one more slide, maybe two more slides. In 2016, large earthquake waves attacked Kumamoto's prefecture, which is located in the Kyushu island to the far west of Tokyo. Now I'm going to introduce the seismic isolated hospital located in this area. At the 2016 Kumamoto earthquake comprises two large earthquake events that occurred separately in 28 hours, which is an unprecedented earthquake in our country. Extremely large ground motions were induced, and many houses and buildings were collapsed or severely damaged. Large landslides also occurred. These are the damaged buildings. This is Aso Medical Center in Kumamoto Prefecture. This building is supported by 45 red rubber bearings and 27 natural rubber bearings. The function of the medical center was maintained during and after the earthquake by the seismic isolation system. The locus of the isolated movement was recorded, and this building on the scratch plate. The maximum displacement of the isolator was 46 centimeters. This is the largest displacement ever observed in Japan, as far as I know. So because time has come, so I will skip this one. And in Japan, long period, long duration, and earthquakes movement was the topics for the design of isolated buildings. We are now main design topics this long period, long duration earthquake and motions. So ultimate behavior of seismic isolated buildings are one of main topics on seismic isolated buildings design. This is, I will stop my presentation. Thank you very much. This is the end. Thank you very much.
Thank you very much, Professor Tamura. It was very nice presentation. There are already some questions, but we are gonna save them for the last part after the next presentation. I will then present the next speaker, Akitsugu Muramatsu. Mr. Muramatsu holds a bachelor and master degree from Kyoto University, and he's currently the chief manager of the design division at Taisei Corporation. Within Taisei, Mr. Muramatsu has an extensive experience in the structural design of various types of buildings, including tall buildings, seismic isolated buildings, buildings with response control systems. In addition, he's the member of the Japan Society of Seismic Isolation in the Committee of Foreign Affairs, and a member of the Committee Overseas Expansion for Newly Developed Technologies in Japan. Please welcome Mr. Muramatsu, and the session is yours now.
Thank you very much, Mr. Luis. Okay. Okay. Thank you very much for giving me this good opportunity to communicate with Peruvian engineer and researchers. This is my presentation title, Examples of Seismic Isolation Response Control Buildings in Japan. So first of all, my name is Akitsugu Muramatsu. I'm a structural engineer from Taisei Corporation, which is a construction company based in Japan. And I started my career as a structural engineer since 2000. So these are today's topics. So first one is introduction, and the second one is outline of seismic isolation building design in Japan. And then I'd like to introduce two SI buildings. In my presentation, the word of SI means seismic isolation. And I'd like to introduce one building with response control system. So this is the first topic. So this is the background of my presentation. The past earthquakes revealed gaps between the performance defined as minimum requirement by law and the performance potentially expected by society. This table shows the minimum requirement performance and the expected performance according to each earthquake level. There are gaps between two sets of performances. Usually expected performance is higher than minimum requirement. For example, this is a point option. Japanese code does not define the performance of this earthquake level, but naturally, society expects us to design buildings with enhanced performance against beyond design basis event. So we structural engineers are expected to meet not only the minimum requirement, but also the society's potential expectations. So what can structural engineers do in order to implement the expected performance? Of course, within limitations in projects. In the right column here, Some examples to achieve the expected performance are listed. For example, to provide redundancy with buildings is one of solutions against beyond the design basis event. So from these points of view, I'd like to introduce some buildings with SI system or damping systems. So this is the second topic, outline of seismic isolation building design in Japan. And this figure shows the number of construction of SI buildings in Japan. So the vertical axis shows the number of SI buildings. The horizontal axis shows year. So until 1995 here, the number of SI buildings was not so much. In 1995, a large earthquake occurred, Kobe earthquake. After that, many people learned that the performance of SI buildings to protect lives and properties was impressive. Then the number of SI buildings rapidly increased after the earthquake. Here and here. Although there are a few sharp increases right after major earthquakes, the average number of construction of SI buildings were about 150 in last 2 decades, about 150. So as of 2017, the total number is over 4,500, and our company has constructed about 10% of SI buildings in Japan. So I'd like to show some features of SI buildings design in Japan. I learned some materials about your country's seismic codes, which seemed to be similar to the United States design code. So I'll introduce some points comparing with the US seismic design code, AC 7-10. And I learned that your SI design code has already complied with AC 7-16. So comparison with AC 7-10 may be a little bit different from your current code. So as of design procedure, 2 procedures are allowed to design SI buildings in Japan: static procedures and dynamic procedures. Japanese static procedure equivalent linear method is similar to the US static procedure, equivalent lateral load method. As for dynamic procedure, nonlinear time history analysis is allowed in the seismic design code. Static procedure is very simple and useful, but there are several restrictions on application of static procedures. So usually, nonlinear time history analysis is widely used for design of many SI buildings in Japan. And this is a comparison of return periods of earthquakes for design. 2 levels of earthquakes are defined in Japanese seismic design code. From the practical viewpoint, all structure members and isolation system are designed using 500 years earthquake. On the other hand, although all structural members are designed using about 500 years earthquake, isolation systems need to be designed using about 2,500 years earthquake in AC 7-10. So this may require bigger displacement capacity than one required in Japanese seismic code. So as for typical type of SI systems usually consist of isolators and dampers. There are various kinds of device which we can choose, such as rubber bearing, sliding bearing. As for dampers, oil damper, steel damper, and lead damper, and so on. And adequate devices should be selected to mitigate seismic response efficiently according to each building's type, use, and required performance. And this slide shows some common types of SI systems. Blue boxes indicate isolators, red box indicate dampers, and orange boxes indicate bearings, which have both functions of isolators and dampers. Type number 1, 2, 3, and 4 are popular systems in Japan. On the other hand, type number 3, 4, and 5 are popular systems in the United States. Type number 2, the combination of natural rubber bearing and flat sliding bearing, is our company's original system. So we call it a hybrid TAS system. A good point of this system is to easily achieve longer natural period of SI buildings in comparison with other systems. So, okay. This video shows dynamic tests of natural rubber bearing. So isolators can smoothly deform in horizontal directions and can support vertical load under large horizontal deformation. This is also another video about sliding bearing. And this video shows the dynamic behavior of the hybrid TAS system during an earthquake. So left side is SI building, and right one is non-SI building. The black bearing are natural rubber bearing, and these white one are sliding bearing. You can see the big difference between two buildings' behavior. And the good performance of the hybrid TAS system has been proved by past large earthquakes. These photos were taken in two hospitals buildings, which were next to each other. Left one is inside of a non-isolated building, and the right one is inside of an isolated building. You can see the big difference between two photos. And if you were a doctor, how would you work under the left photo's condition after earthquake, sorry. The isolated building kept operational right after the earthquake. Keeping operational right after earthquake is one of the great benefits of SI structures. So this is the next topic. I'd like to show one example of short stroke SI system with passive switching oil damper. And this is the background why we have developed this short stroke SI system. So after several major earthquakes in Japan, demands for SI systems are continuously growing, as I mentioned in the figure in the previous slide. Even for buildings in relatively small size, often located in densely urban area like Tokyo or Lima, SI systems are highly required to protect property and operational function and to achieve companies' business continuity plans or BCP. In order to implement a SI system in small site, response displacement of isolation layer due to major earthquakes needs to be mitigated for keeping buildings area as large as possible. As for conventional SI buildings, design clearance between building and the moat wall is usually 60 centimeters or so. In relatively small site, if we wanted to keep same clearance of 60 centimeters, possible building area were reduced. So by mitigating the response displacement of isolation layer, we can keep buildings area as large as possible. So large damping is necessary in order to mitigate the response displacement. So as for building response due to major earthquakes, if we install large damping into the isolation layer, we can prevent collision. But as for frequent minor or moderate earthquake, large damping will result in large response acceleration. This may be not good isolation performance. So normal damping may be good, in order to mitigate response acceleration due to minor or moderate earthquake. So normal damping is preferable to large damping for minor or moderate earthquake, but large damping is necessary in order to prevent collision during major earthquake. So this is the issue to be solved. In the case that the site is not spacious, to mitigate response displacement during major earthquake by large damping is necessary. But to reduce response acceleration during moderate earthquake is also required, and this is a contradiction. So we employed viscous damper whose properties can change. The variable damping means lower damping coefficient for moderate earthquake and higher damping coefficient for major earthquake. So we developed a passive switching oil damper. This is a kind of variable viscous damper. The passive switching oil damper has a special characterized damping coefficient, which is switched from low damping to high damping after exceeding a designated displacement. To acquire the special character, some parts for detection of displacement shown in red is here, are added to a conventional oil damper. This figure shows damping properties of passive switching oil damper. Vertical axis shows damping force, and horizontal axis shows velocity. So this damper has two modes. One is a lower damping mode, which is assigned to initial condition. Another one is higher damping mode. The damping coefficient is switched from the lower one to the higher one after exceeding a designated displacement. In this project, we set 10 centimeter as the designated displacement. This displacement can be changed according to each project. This passive switching oil damper has high reliability. The damping coefficient is mechanically switched from lower to higher without electrical power. So this leads to high reliability and easy maintenance. And the shut-off valve keeps closed once switched. So after earthquake, the initial low damping mode is recovered by using manually operated lever. So this is a summary of merits of passive switching oil damper. The first one is low damping coefficient result in full demonstration of isolation performance during moderate earthquake. And high damping coefficient result in mitigation of response displacement during major earthquake, including beyond design basis event. So safety is ensured during major earthquake without compromising the sense of security during moderate one. We applied this system to a few buildings. I'd like to introduce one example, which is called ZEV demonstration building. This is a SI building with the passive switching oil damper, which is newly constructed in our technology center. This slide shows the structural systems. This is a 3-story building. Isolation layer is here. And the lateral force resisting system of superstructure is moment resisting concrete frame with concrete shear wall and very slender column with high strength concrete of 300 megapascal is gravity element. And this slide shows the structure plan in the first floor. In spite of uneven distribution of lateral stiffness due to the slender columns located in one side, torsional behavior is significantly mitigated by adapting the SI system and arranging the lateral force resisting system in the channel shape. And this photo shows the entrance hall, which can get open and spacious by adapting the slender columns. And this slide shows the plan of isolation layer. The isolation system composed of natural rubber bearing, red one, and the flat sliding bearing, blue one, and the passive switching oil damper, a green one. The design clearance between the building and the moat wall is 300 millimeter, which is almost half of the typical clearance of conventional SI structures. Okay. And this is a parametric study with single degree of freedom system to evaluate appropriate damping coefficient for moderate earthquake. Two parameters are employed. First one is earthquake level. Another one is damping coefficient. So vertical axis shows the response acceleration, and the horizontal axis shows the response displacement. And this line, this red line, shows the this line shows response with the half of major earthquakes. If more damping is added, the response acceleration becomes larger here. And if damping is reduced, the response displacement becomes larger. In this project, the response with the lower damping mode is better in order to acquire a smaller response acceleration for moderate earthquake. And this is a comparison between passive switching oil damper and conventional oil damper. So right figure shows the damping properties of oil dampers. Black line shows the property of conventional damper, and the red line shows the property of the higher damping mode of passive switching oil damper. The left figure shows the result of nonlinear time history analysis with stick model and major earthquake. The horizontal axis is maximum response displacement. As for response with major earthquakes, the maximum displacements are almost the same and enough smaller than the design clearance of 30 centimeters. And this is also another comparison. Right figure shows damping properties of oil damper. Black line shows the property of conventional damper, and blue line shows the property of the lower damping mode of passive switching oil damper. The left figure shows the result of nonlinear time history analysis with stick model and moderate earthquake. The horizontal axis is maximum acceleration. As for the response with moderate earthquakes, the maximum acceleration with passive switching oil damper, it decreased significantly by 30 to 40% in comparison with the result of the conventional oil damper. And this building also employs a seismic observation system. The accelerometers and displacement sensors have been installed in the building. And after earthquakes, recorded data are automatically analyzed and the results are automatically reported by email right after earthquakes. So building owners and engineers can get useful information about whether or not it is necessary to investigate the building more closely. And this slide shows an example of the automatic report. The red line shows the recorded acceleration in the main buildings, which is not a SI building. And the blue line shows the records in ZEB, which is next to the main building. So you can see the effect of seismic isolation is fully demonstrated. And the short stroke SI system with passive switching of the damper has been applied to some buildings in Tokyo. The center one is an application to a high-rise building. And the right one is an application to an existing building of a local government. And this is a summary. Safety is ensured during major earthquakes without compromising the sense of security during moderate earthquakes. And the system allows owners to adapt the SI system in urban sites while keeping the building area as large as possible. And here, this is the next example. Another example is high-rise building with semi-active isolation system. This slide shows outline of semi-active isolation in chronological order. When an earthquake occurs, sensors inside and outside the building catch the vibration. Then a computer starts calculation to get an optimal damping force according to the information from sensors. Computer controls damping force of oil dampers to mitigate shaking of buildings. And the semi-active isolation system has been adapted to this high-rise building. The height of the building is 130 meters. This building was constructed before the Tohoku earthquake in 2011, so we got some observed records. These red square marks were recorded maximum acceleration, and the white square with red line are the result of simulation. On the other hand, blue line is a result of simulation if this building was not a SI building. So the semi-active isolation system can significantly reduce the maximum response acceleration. The acceleration value at a few floors are listed in this table. The ground acceleration was 97.7, and the response acceleration were 29.2 and 46.1 centimeter per square second in basement first floor and roof floor respectively. So accelerations were reduced to 1/3 at basement first floor and 1/2 at the top of building in comparison with acceleration at the ground. And the occupancy of this building is a private school. Most students did not think that such a huge earthquake occurred thanks to isolation effect. And by adopting the semi-active SI system and the mega structure system, this building has a lot of flexibility in design. This is a sky garden, and there are no columns which obstacle the nice view from the sky garden. This is a view from the sky garden, and this is also another view. And the classrooms are wide and spacious with the columns. And this is also another spacious area in the first floor. So by adapting the semi-active SI system, this high-rise building has high seismic performance in addition to high flexibility of planning. Next topic is an example of building with response control system. So this example is response control system with shear wall coupling and the coupling beam. This is a background why we have developed a new response control system with shear wall and coupling beam. The performance demanded of the latest buildings are diversifying, such as safety, security, environmental protection, long life, and flexibility of planning. So it is necessary to develop new response control system, which we call TASMO. Our buildings with the new system were expected to have high seismic performance and long life with flexible space. So this slide shows the concept. And this slide shows the usual response control system. This system consists of main seismic force resisting system and damping systems. The damping devices are installed in parallel configuration with the main seismic force resisting system. So about 20% of the total seismic force is imposed on the damping devices. On the other hand, this slide shows the concept of TASMO. This system consists of wall column and steel damper. So the steel damper are installed in series configuration with wall columns. So all seismic forces go through the steel damper. This shows each element which is used in the system. Wall columns, or which are also called coupled wall, and coupling beams, which are steel dampers. Low-yield steel is used to absorb seismic energy effectively. And oil dampers are also installed at the bottoms of wall columns. But main energy dissipation devices are steel dampers. We applied this system to several buildings. I'd like to introduce one example where we applied this system to our branch in Sapporo, in Hokkaido. This is an office building with structural design concepts listed here. A long service life, high seismic performance, column-free inner space, and a new structure framework. And this slide shows the building plan. The occupancy of this building is office and shop, and the length of long side is 39.6 meters, and short side is 18.6 meters. And this is a building section, 8 stories above ground and 1 basement floor. And the height is about 35 meters. And this slide shows outline of the structure. Reinforced concrete wall columns are set around the perimeter of the building. And those wall columns are connected by coupling beams, which work as steel dampers. In order to prevent the collapse of the building, coupling beams at the top floor are designed to keep elastic even in case of major earthquakes. In order to achieve column-free inner space, precast press-rest concrete beams are used. The span length is 18.6 meters. And this slide shows the close-up of the bottom of wall columns. You can see the coupling beam and the oil dampers are absorbing energy when wall columns move. As for materials of steel damper, we adopt low-yield strength steel, which has lower yield strength and greater ductility in comparison with normal strength steel. Steel dampers can effectively absorb seismic energy by yielding early. The ductility performance of low-yield steel has been examined by dynamic tests. This video shows one of the dynamic tests. So the low-yield steel dampers has great ductile performance, and you can see the wave plate deforming by shear force. This slide shows an analysis model for nonlinear time history analysis. The wall columns and the coupling beams are modeled as beam elements with nonlinear property. Natural periods of the building are 0.725 seconds and 0.951 seconds in long side direction and short side direction respectively. And this slide shows absorption of seismic energy by each component. A vertical axis shows cumulative energy and horizontal axis shows time. This bold black line. This bold black line. This bold black line shows input seismic energy over large earthquakes with 500-year return period. The total energy dissipation by wall columns is about 10%. Moreover, hysteretic energy of wall columns is about 3%. That means a structural damage on wall columns is expected to be very limited. On the other hand, energy dissipation by all dampers is about 90%. Especially steel dampers absorb about 70% of input energy. So steel dampers are expected to work effectively against earthquake. To achieve column-free inner space, precast press-rest concrete beams are used. This slide shows some details of the precast press-rest beams. The span length is again about 80.7 meters. And the beam depth is 750 millimeters. and high strength deformed reinforcement bars is used as tendon. And this is a photo of precast pressurized beams. You can find that there are no anchor devices at the end of beams. This is so-called pretensioning system, so which is competent in the viewpoint of cost because of no anchor devices. The pressurizing force of tendon is transferred to concrete by bond between tendon and concrete. And this is a photo of inside of view. And this is a front elevation. These are oil dampers. And this is a coupling beam, which work as steel damper. Low yield strength steel is used for web plate. And the shear strain of web plate are monitored to examine the integrity of the building. And this is a summary. The steel dampers and the oil dampers are incorporated so that these devices act effectively and high seismic performance can achieve. The soundness of the steel dampers and the whole building can be monitored in the distant place. And precast pressurized concrete beams are adapted to obtain flexible inside space and use the concrete surface as finishing. And this is another important topic. Good seismic performance cannot be achieved without good quality control of manufacturing and construction. Every single device has to be tested and reported to structural engineers before its installation. And I'd like to show some photos on tests of devices. This photo shows a static test of a lateral property of natural rubber bearing. And this photo shows measurement of some dimensions of the isolator. And this photo shows a static test of lateral property of flat sliding bearing. And this photo shows measurements of some dimensions of the sliding plate. And quality control of construction site is also very important. Accuracy of installation has to be inspected and reported on time. The design clearance between the building and the moat wall has to be confirmed after completion. And the design clearance between the building structure and the piping also has to be confirmed after completion. And these are also important points to keep building function after earthquake. A confirmation of the flexibility of piping and the confirmation of the extra length of the electrical wires. And this is the final slide. This figure shows a cost comparison between non-SI building and SI building. Non-SI building is left and SI building is right. Usually structure cost is slightly reduced by decreasing of lateral force. But repair cost after earthquake is significantly reduced because SI building can protect structure, non-structure, and contents. And as for typical SI related cost, it is about 2 to 5% of total initial cost here. It is very small increase in comparison with total initial cost. So let's say about 10-story office building. Structure cost is about 20% of total initial cost in typical. And SI related cost is about 10% of structure cost. So SI related cost is about 2% of total initial cost. So what if you consider repair cost after earthquake? SI systems are really cost-effective system, especially in earthquake-prone country like Japan or Peru. So why don't you choose SI system? And I'd be very happy if my presentation could be some help to you. Thank you very much for your kind attention. Muchas gracias por su atención. Thank you.
Thank you very much, Mr. Muramatsu. It was a very nice presentation. Now we are going to move into the question session. So we already have some questions here. I'm going to pass some of them to you. First to Professor Tamura. There are kind of common questions here about, for example, Professor Tamura, how do you prevent retaining wall collision and uplift in seismically isolated tall buildings?
Yes. The first method is to make a margin in seismic isolation layer. That is the design so as to make the deformation become large. So that is one one method. And sometimes some designer can adopt shock absorber in retaining wall, but it depends if the earthquake ground motion becomes large, it does not work so well. I think so. It's not so effective in case of that case. So usually we use the design level to have a margin, some level of margin. It's I think it's the best for me. It's the best selection. I think so.
Thank you very much. We have a question to Mr. Muramatsu.
Yes.
They say you gave an example of semi-active system. How expensive is it compared to passive system, and how is the maintenance of these systems about?
Yeah, actually, it's a little bit expensive in comparison with conventional seismic isolation system, because that system needs a monitoring system, computer devices, and some accelerometers. So, but please consider the total cost of buildings. The SI-related cost is not so much. So I think the most important thing is building owners' understanding. If they consider the building is very important, that system, I think that system is not so high, too much expensive. But actually, it's a little bit expensive to conventional SI systems.
Well, thank you very much. We have a question here from Javier Piquet. Which is the role of isolators in high-rise building, since they work lengthening the period? A tall building already has a long period. I think this question is for both of you. Any word on that?
Okay. I have a paper about that topics. Can I share this? Okay.
Sure. I think you can send a link in the chat box, or.
Oh yes. Okay. Can you see can you see the paper?
Yes, we see the document you are sharing in.
Oh yes. This is a paper about the development and the realization of base isolation system for high-rise buildings. This is a study about the base isolation system for high-rise buildings. There are a lot of discussions about these topics in late 90s and early 2000s in Japan. And this is one of the study. And in this study shows some parametric study about here, and I have I have another slide, and I think this is more easy to see. And this slide shows the response reduction effect of base isolation system has been assured by parametric analysis. And in this study, the researchers use the analysis model, this kind of stick model. And this spring one shows superstructures property, and spring two shows base isolation story properties. And this is the result of parametric study. You can see this left figure. And vertical axis is response ratio. Response ratio means response of base isolated structure divided by response of non-base isolated structure. And the horizontal axis is a natural period of superstructure. And usually about 100-meter tall buildings has a natural period of about 3 seconds or 3.5 seconds. And in this case, you can see the big reduction effect, even if the building has a longer natural period. And this is one example of application of SI system to highlight very high-rise building. And this building has a 135 meter. And you can see this is the maximum response story drift angle. So you can see the big difference, the response of SI building and without SI conventional building. So I think it depends on the performance. It depends on the required criteria. But you can use SI system to reduce the response drastically, even in the case of tall building. Thank you.
I want to add some comments on that provided by Muramatsu-san. And in the case of a tall building, and of course, the period fundamental period becomes longer. So the seismic isolation effect was reduced, and comparing with the lower rise or middle rise building. But seismic isolation, by using seismic isolation, the fundamental period can lengthen even in the case of a tall building. So the seismic isolation response is more smaller level than the taller building. So we anyway, this is my additional comment.
Yeah, thank you very much.
Thank you very much to both of you. I think we have more questions here. I think this is particular to Professor Tamura. It says, could seismic isolation systems work in conjunction with performance-based seismic design?
I'm not sure. I'm not so sure on performance-based seismic design, but seismic isolation may become one of menus of design. But the question, I can't understand the question, performance-based seismic design. But I think maybe seismic isolation becomes one menu. But the question is the different question. I can't understand that.
Yeah, and apparently there is no more comments on the within the question. So I guess that we can move on to another question.
Okay.
Yeah, there is another question to Muramatsu-san.
Yes.
What do you think about the 3D seismic isolation systems?
3D seismic isolation systems. Yeah, it's very nice. But sorry, I'm not so familiar with that system. But in Japan, I think maybe a few buildings which has been almost installed such a 3D isolation system. But I think those buildings are all small buildings, not so large, not so high-rise building. And yeah, 3D system is very nice, but I think we need to more study and reduce the cost of those systems to apply many buildings.
Okay.
I want to, if possible, I want to add that I participated in the design of the 3D base isolation system, and 3D isolation systems design is very difficult because one is very difficult because the vertical direction response should be reduced by using large dampers, and also if the design can be possible, it becomes very not expensive one. So it is very difficult. We want to develop very cheap 3D system, but I think it's very difficult. Yeah.
Okay, thank you very much. We have one more question, a kind of long question. I'm gonna try to summarize it. So it basically talk about the most seismic events are generated in subduction zones and active faults. The earthquakes produced by an active fault are characterized by the presence of velocity pulses. Research has demonstrated that impulsive ground motions with velocity pulses are more destructive for traditional structural systems. How are the base isolated buildings affected due to impulsive ground motions? Is the effectivity of base isolation system reduced during these velocity pulse motions?
Velocity, I'm sorry, I can't understand. Velocity, what? Velocity?
I think they are, I guess they are meaning the close distance ground motions. Maybe related to the kind of the Kobe ground motion record, which
very impulsive, large amplitude motion, you mean so?
Apparently it means that.
So very, it's also very difficult to answer. 3D seismic isolation more difficult than 3D seismic isolation. In case of impulsive large amplitude long period ground motion, the effect of seismic isolation becomes effect becomes smaller. So if the that kind of ground motion will be happened, in case the design should be made in the total manner, maybe seismic isolation may not be the best selection. I think sometimes the strengthening of the upper structure should be also made to the structure. So it's very difficult to answer. How about Muramatsu-san?
Yeah, I think it is a very difficult problem. if we deal with such an impulsive ground motion, we need to a very high, too much damping in the SI system. So I think, yeah, it is very difficult to answer. Yeah.
In case of such input motion, the damping effect is also
not working
effective,
properly
yeah.
working. Yeah, right. Actually, very large displacement was observed in Kumamoto earthquakes.
Okay, thank you. Is there any other question from the audience? Apparently not. So I don't see any other questions, so I would like to thank the speakers, Professor Tamura and Mr. Muramatsu, for the very bright presentation you provided. And as a closing remarks, I would like to invite once again to Dr. Flores to give last words before concluding the event.
Professor Tamura, Mr. Muramatsu, thank you very much for joining us for our last webinar series of the year. We have closed these seminars with a golden note. We very much appreciate you sharing with us your experience with these isolation systems. I am sure most of us are leaving this webinar with some ideas that we may want to use in the future. Thank you very much for your time, Professor Tamura Muramatsu-san.
Thank you very much.
Thank you very much.
Thank you very much. And to all the audience, once again, thank you very much for having joined us throughout all this year. Just a very quick reminder that you can find all our previous webinar series in the website of our main page. Sorry, I'm going to copy the link here in case you're interested of following those. And we look forward to meeting with you again next year when we are going to continue learning together in these strange Corona times. Thank you very much. Thank you very much to everybody.
Thank you very much to everybody. Good evening and good morning there in Japan. Thank you very much.
Yeah. Have a good night. Thank you very much.
Thank you. ありがとうございます。失礼します。
Have you